Okay, class 12. In this video, we are going to talk about motional EMF. So, what we have is, we have this rectangular frame MNOP, okay, and this strip or rod OP is movable over the frame. It can move left and right. And by the way, we have a magnetic field which is perpendicular to the plane of the board and going into the plane of the board, as you can see by the crosses here. Okay, so the magnetic field is B. This frame is placed in an external magnetic field, uniform B. The length of the rod or the strip OP is L. The area of the frame MNOP, so this area here, this surface is A. So therefore, there is magnetic field passing through this area. So what is the magnetic flux linked with the area MNOP? The magnetic flux linked is given by phi B, which is B dot A, because magnetic flux is simply the dot product of the magnetic field and the area. So this is BA cos 0 degrees because the direction of the aerial vector, don't forget, is given by a unit normal perpendicular to the plane itself. So the unit normal is going in that direction perpendicular to the frame itself. So it is 0 degrees, the angle between the magnetic field and your area, so therefore phi B is BA. Now what we do is, so this is the initial scenario. Now what we do is, since this frame, this strip is movable, so we apply a force F and we move this strip towards our right hand side with a velocity V. We apply a force F and it is moved in this direction with a velocity V. And let us suppose that the strip OP, let me extend this a bit, the strip OP reaches over here, a new position. Let us call this O dash P dash. Okay, and it moves by a distance, say for example dx. Dx is the distance by which it moves towards the right hand side. So when this strip moves towards the right hand side, what is happening? What is happening is the area is changing. So since the area changes, the magnetic flux linked with the area is also changing. Alright, so whenever the magnetic flux linked with the area on the whole changes, we know from Faraday's laws what happens is an EMF is induced. Okay, so therefore the induced EMF is given by E is equal to minus d phi B by dt. Now the minus sign only tells us that the direction of the EMF induced is opposite to the cause producing it, or it wants to oppose the cause producing it simply. So therefore, this can be written as modulus of d phi B by dt, because here right now we are only interested in the magnitude of the EMF. So, shall I erase this part? I can hear you all saying yes. Okay, so E is that much, so E is modulus of d phi B by dt. I'm rewriting it again. So this is equal to modulus of d dt of BA bar, or E is equal to, please follow the mathematics. Now see, since we've already said the magnetic field B is a constant, so therefore B can easily come out of the differentiation. I almost said integration. So therefore B ddt of A. Alright, now what is dA? A is the area, so dA has to be the change in the area. Now what is the change in area? Alright, let us call this equation number 1. Now the change in area dA will be how much? We've said the length of OP is L and it moves by a distance dx, so therefore the change in area dA is L into dx, length into breadth. So this is our equation number 2. Therefore, from equations 1 and 2, let me erase the lower half, lower part. Okay, and we get, therefore, E is B L dx by dt. Now, what is dx by dt? Dx by dt is the speed or the velocity with which we are moving the strip OP towards our right hand side. There's the distance it moves and in time dt. So therefore dx by dt has to be the velocity v. So thereby we get, therefore, so to say, E is BLV. This is the expression class 12 for the motional EMF. That is, this is the magnitude of the EMF that is induced in this conductor OP when the magnetic flux linked with it is changed. We've seen that the magnitude of the motional EMF or that of induced EMF is E, which is BLV. Now let us also see what will be its direction. So to say, what will be the direction of the induced current? Let us also see that. Now since our strip OP or the rod OP is moving towards the right, so we know the direction of the induced current is given by Fleming's right hand rule. And by the way, I forgot to show here, the magnetic field is perpendicular to the plane of the ball. So magnetic field is given by our forefinger. The force is given by the thumb, so the middle finger gives us the direction of the current. So current on this strip OP or the rod OP is induced in the upward direction. So to say, current I flows in the upward direction. That is, the EMF is like this. The induced EMF is like this. You have a positive side here. It's like the rod is acting like a battery now. Okay? Or you have a battery inside the rod itself, where this is the positive side, is the negative side, such that the current flows in the upward direction.